Hello, maths people. I am sorry I can't be with you, but you get a digital version of me instead. Hum in, close your laptop. All right. Today we are going to start chapter 8. So this is following on from the differentiation topic that we've already done. What we're going to do is use the derivatives in a way that we started talking about last time. So I'm just going to give you a bit of an example about why this works. So we know something like this. We can easily plot that and we can figure out when the function is increasing and when the function is decreasing. Hopefully you can find the x solutions to this. The two numbers that add to the middle and multiply to the last are 6 and 4. So what that means is the x-intercepts are -6 and -4. So if I drew the graph, wow, that is absolutely not what this graph is going to look like. Let's try that again. Okay, so -4 and -6, let's say that's what that is. This graph is going to look like that. So what I'm now going to do is show you using the derivative when I can tell that the function is increasing and when the function is decreasing. Now, I'm just going to prove something to you, but hopefully you can see that the turning point must be halfway between these 2 points, which makes it -5. But if you remember from last year, we say the x-coordinate of the turning point is -b over 2a, which in this case is -10 over 2, which is just -5, which we can already see from the graph itself. So I'm going to prove to you the same thing using the derivative. So if I want to derive this equation, I say dy dx is 2x plus 10. Now, if I solve for this, if I want to say what is my x value at this point, so when the derivative of 0, so remember the derivative is measuring the equation of the gradient, and the equation of the gradient at a stationary point is 0. So what is the x-coordinate when the derivative is 0? Well, hopefully you can see that if I just do my normal algebra, I'm going to get the same answer. X is -5. This is saying what is the x-coordinate when the derivative is 0, which is the same as the turning point. So if I now wanted to get some new information from this, I can say that so what I want to know is when is this graph increasing and when is this graph decreasing? Hopefully you can see here this graph. So think about the gradient, right? This is going, so actually what I'm going to do is use this bit first. Okay, so I'm going to draw this little graph. So if we have another graph and we have here x is -5. Okay, so when x is greater than -5, oh, I've used the opposite colors, that's stupid. When x is less than -5, which is this part of the graph here, oh, I've realized you can't actually see my cursor when I do this, can you? Right, anyway, that's why I'm color coordinating. The green bits, when x is less than 5 on the red graph, and when x is decreasing on the blue graph, you can see that's what that graph is telling us. So if I change colors here, when x is greater than -5, what I'm saying here is that the graph is increasing on the original function. So when when the value is more than 0, then the graph is increasing. When the graph is less than 0, the derivative graph is less than 0, the function is decreasing. So that's what we're going to use this for. Okay, let me just save that and let's do an actual example with something harder than a quadratic. I just wanted to use a quadratic to show you what's going on. All right, let's get a darker color. Okay, so this time I'm going to say, yeah, let's not use a quadratic. Okay, so y equals 4x cubed minus 15x squared minus 72x minus 8. Okay, so I want to know when is this function increasing? So let's do some color coding. I'm going to find out when it's increasing and I'm going to find out when it's decreasing. So let's do increasing first. So just like I did before, I need to find my gradient and then graph that to figure out whether my values are positive or negative. So let's first of all do, actually, I'm not going to color code that yet because that's not helpful. Let's go back to this. So dy dx. All right, so you can see bring down this becomes 12x squared minus 30x minus 72. Now I need to well, what I'm going to do first is take out a common factor. I'm going to take out, what can they be divided by? 6. Okay, let's take out 6. So I get x squared minus 5x minus 12. Sorry, I need a 2 in the front, don't I? 2x squared minus 5x minus 12. So if I want to factorize this, again, you can factor it or you can use the quadratic formula. I know I need one of each sign. This is going to be plus 3 and minus 4. That'll give us negative 12. 2 times negative 4 is negative 8, plus 3 is negative 5. So that means my x values are negative 3 on 2 and positive 4. So if I graph this, I've got 4 and negative 1.5. And it goes through negative 12. So that's going to be somewhere down here, whatever. Okay. So what I want to do is let's do the positive values first. So I'm going to color code red this time. So the graph is positive in this direction and in this direction. That is when the value of the function is greater than 0. So that means x must be less than negative 3 halves, right? It's going less than, or x has to be greater than 4 because that's when it's going up forever. Those are the two parts. I know that, no, I'm not going to say that. That'll be confusing. So what we're doing is we're looking at the graph of the derivative. When is the function increasing? When it's greater than 0. And when is the function decreasing? That makes it negative. So it decreases in between these two values. So the value of the function is decreasing when x is between these two values, when it's between negative 1.5 and 4. Notice I don't have an equal to sign here because at these points, these are the turning points. This, let me change colors again. This is a positive quadratic graph, positive cubic graph. What we've just done is found these two turning points. This turning point here is the first one, and this second turning point here is the second one. That's what we're doing here. We're looking at, so let me color code again. So for the parts of the graph, where is it increasing? It's increasing here and here, right? That's when the graph has a positive gradient, when the graph of the gradient is greater than 0. And when is the graph negative? Well, the function is negative. It should be curvy. I'm not drawing a straight line. When the graph is curvy, when the graph is negative, it's the same as when the graph of the derivative is below 0. Okay, I hope that makes sense. So that's what you're doing today. You are graphing equations. You are finding the values of x for when the function is either increasing or decreasing. Sometimes you will need to, like I find it normally helps to draw a little graph just so you can see it better. But I recommend that you do try and draw it as much as possible. Especially drawing the derivative. You don't necessarily have to draw the original graph. I was just trying to prove a point to you. All right, good luck with exercise 8A.